responses. Now next we start with the Windows-based FIR filter design. In case of the Windows-based FIR filter design, most of the steps as we are following in the Fourier series method, that is computing up to HD of n, will remain common, and there will be an addition in terms of the window based functions. So in this case, the design step follows as here. So initially we are assuming an ideal desired frequency response. So throughout we are having a suffix of D for both capital H and small h, where this D stands for a desired frequency response and desired one is an ideal response. Hence is the HD for omega, that is frequency domain also, and for the time domain also. So we have seen that the HD of omega, the frequency response, is expressed in terms of these Fourier coefficients, that is HDN. So this is basically the formula of discrete time Fourier transform. And in order to obtain an unknown, that is the impulse response of the FIR filter, we are applying the inverse discrete time Fourier transform to this HD of omega. The fact is, since we knew for low pass, high pass, band pass and band stop how the frequency response nature is, so this part is known to us in terms of frequency responses, and throughout it has got a unity magnitude. So we are simply replacing this with, in the later phase in designing, we are replacing this term with a unity magnitude, and in the integration limits we are substituting the appropriate cutoff frequency values according to the type of filter. But in general, HDN will be computed as 1 by 2 pi integration from minus pi to plus pi h of omega into the basis function e raised to j omega n d omega. Now to find out a causal filter from HDN, we have to define a new impulse response set, that is h of n. We seen earlier that HDN is having the range of n from minus to plus infinity. It means this impulse response contain infinitely long impulse response coefficients, which we are truncating, because that one is HDN is the response, the impulse response of an ideal filter. So we are truncating it to the finite length so as to practically handle that impulse response coefficient values. So just by truncating it, as h of n is given only a selected values of impulse response in the range of 0 to m, and otherwise we are putting it up as 0. So these are the initial steps. Followed by this, now how to perform this truncation. Now in order to perform this truncation, we are multiplying the HDN, which is infinitely long, with a finite duration window functions Wn, and this multiplication will lead to the impulse response with finite length duration. So this Wn, the window function, is again a finite duration window function, and Wn are termed as window coefficients. A very basic form of window function is a rectangular window, and rectangular window mathematically is expressed as Wn with a unity magnitude in the range from 0 to capital M and is 0 otherwise. So this window function, when we are multiplying it to HDN into time domain, this multiplication will lead to the convolution in the frequency domain, and the convolution will be between the convolution of hd of omega and w of omega. So this is the expression which is also called as a modulation theorem or a convolution theorem. So this is an entire formula, and which ultimately means we are performing the frequency domain convolution for this time domain multiplication. Now this frequency domain convolution will take place as shown, that this is the sinc form is basically the frequency domain characteristics for a window function. Say basically when we consider the rectangular window function, the rectangular window function after taking its discrete time Fourier transform will take up a form of sinc function. So this is basically a frequency domain or the discrete time Fourier transform of window function, which is then multiplied, which is then convolved with this frequency response of an ideal filter. So here with this square block, it indicates basically the ideal filter frequency response. And following the usual procedure in the convolution, as one of the segment is kept constant, the other segment will keep shifting, and during the shift there will be a multiplication and finally the addition between the terms. But remember that this convolution is taking place in the frequency domain. Ultimately, the result is shown in the final graph, where we see that the frequency response h of omega is resulting as shown by the arrow and by this frequency response plot, the thick line, which indicates there are ripples present in the pass band, and then there are ripples present in the stop band also, as a result of this procedure of convolution in frequency domain